Alright, so last time we left off, we talked about how H3PO3, even though it has 3 hydrogens, it's diprotic because one of the hydrogens is connected to the phosphorus, and hydrogen and phosphorus have similar electronegativity, so this hydrogen will not ionize. Only these two will ionize. That was the answer of part A. It's because the electronegativity difference between phosphorus and this hydrogen is not that great. Alright, we did B as well, right? Okay, the one that, okay, so just make sure that you guys have your answer for B, because you're gonna need that in order to solve for C. One of the aspects of C, you're gonna need B. Alright, so let's start C, and this is where I made the goof up last time. But what we're gonna do first is we're gonna take a look at this pH, and what we're going to do is we're first going to calculate the concentration of H+. So I'm going to have you guys take a second, plug this into the pH formula, see if you guys can find the hydrogen concentration. Alright guys, so I got the work up there for you. You guys should got an H+ concentration of 0.026. Everybody good with that? Okay, so we're pretty good at converting pH to molarity of hydrogen now. I also put the answer for B if you guys don't have it written down from last time. The answer for B was 0.032 molarity of H3PO3. And again, we'll be using this for our ice table. Okay, so it tells us, excuse me, to calculate the percent ionization and the Ka1, and we can also assume that the Ka1 is much greater than the Ka2. And so we're going to write the first ionization first because for acids, hydrogens ionize one at a time. So we're going to get H3PO3, and I will give you guys 30 seconds to finish up that first ionization reaction. Alright, everybody good with this first ionization reaction? Oh, H2. Alright, so that would be the first ionization. Now, I'm not going to have you guys do this, so you don't need to write it. But technically, we can take the conjugate right here, H2PO3 minus, and this can also ionize a hydrogen as well, right? And then we would end up with HPO3 2 minus. However, because this is telling us that the Ka1 is much greater, what we can assume is that pretty much all of the hydrogens come from the first ionization. Okay, and when we did the ice tables for the polyprotic acids, you guys remember how the value of H+ was very, very small for that second ionization? What we're going to do is we don't need to do this an ice table for this one because we can just assume the number is really, really small. Do you have a question? Yeah, it's going to be X. We're going to be filling out the ice table now. Yes. Yes. Okay, so we're going to set up our ice table. Alright, and let's plug in the values that we have. So we're going to be using the answer from part B to get the initial concentration of H3PO3, okay, because it's referring to the original solution, so it's talking about the one up here. Okay, so the initial concentration of our acid is going to be 0.032 molarity. Okay, and I'll pause right there, and let me give you guys about a minute or so. See if you guys can plug in the rest of the ice table. Alright, so I filled in the ice table for you guys. Hopefully the change section is pretty simple. It's minus X for the acid, and you're gaining the products. Oops. The equilibrium value for our acid is going to be 0.032 minus X, and these will be X, and then we calculate the pH, or the concentration of H+ from pH, and that's where we get this value right here. Okay. So far, so good? Everybody good? Very similar to what we've been doing. Alright, now the problem is asking us to find two different things. It's asking us to find the percent ionization and the Ka1. Okay, let's start with the Ka just because we have all the equilibrium stuff, so we can just plug it into the equation that we have. So the Ka expression is going to be the concentration of H+, which is X, and we see that X is 0.026, so 0.026, and there's two of them, so we're going to have to square it because they're being multiplied, divided by this value right here, 0.032 minus x. Okay. So we do have an x, but if you guys see, we already know what the value for x is, right? So we can actually just plug that in right here. So the minus x will become minus 0.026. So I'll pause right there and I'll let you guys calculate for the Ka. Okay, we're just plugging into the equilibrium constant expression and solve. All right, did you guys all get 0.011? Or did I calculate something wrong again? Oh gosh, I thought I was having a good day. Okay, 0.026 squared divided by 0.11. God, my goodness, guys, I'm sorry. I am letting my bloodline down by messing up with simple calculations. All right, so 0.11. All right, so that's Ka. Let's do percent ionization now. So percent ionization, pretty simple. If you guys don't remember the equation, that's totally fine. But for percent ionization, we're going to take the amount of hydrogens that ionized, so 0.026, divided by the initial amount of acid that we had, so 0.032. So this is the hydrogen ionized, so molarity of hydrogen that actually ionized, divided by the molarity of our acid initially. Okay, and then just make sure you multiply it by 100%. So I'll give you guys a second to finish that calculation, and that's it. That's how we can finish up this problem. Yes, because that is what's coming off of the acid. Yeah. So if it's asking for the acid ionization, this is the product of the acid ionization, so you always put the hydrogen on top. Alright, so again, guys, 81.25% is your percent ionization, and that honestly is a pretty good example of an FRQ question. See how we synthesized a lot of concepts together, right? We talked about the structure of acids, we have a little bit of dimensional analysis, and we also have pH, and we have an ice table. So it kind of synthesized a lot of things together. Alright, so we're going to go back to talking about salts. So you guys just make sure you guys are aware of that. So we talked about how when you have a salt, it dissociates into a cation and anion, right? That's where this concept comes in. So what we're learning about is called the common ion effect, and basically this is exactly what it sounds like. It's telling us how it affects the pH when you have a ion that is common between two compounds. So I think it's actually easier to just do a problem than to go over this. So we're going to jump straight into a problem because we actually have the prerequisite skills to solve this already. Okay. So what we are doing here in this problem is we're looking for the pH of a solution, and it tells us that this solution right here, oh god, that's not a good container. Okay, so in the container, we're going to have 0.3 moles of acetic acid. Okay, so HCH3COO, and you have 0.3 moles of sodium acetate, NaCH3COO. What? Do you hear something? It's just in your headphones. Okay, so that's what the solution is made out of, and the solution's volume is 1 liter. Okay, so that's the situation. Everybody good with interpreting that? You got a solution, 0.3 moles of acetic acid, this is the formula, and you have 0.3 moles of sodium acetate. And it's basically asking you the pH. Now, if you guys take a look, we have an ion that the two compounds have in common, right? So we have CH3COO, and that's your common ion. One comes from an acid, and one comes from a salt. Okay. Everybody good so far? Okay. So let's start with our acid. So if we take a look at acetic acid, HCH3COO, what type of acid is this? Weak. Yeah, it's not one of the 7, so this is going to be your weak acid. So let's label it as weak acid. Okay, and let's take a look at sodium acetate, NaCH3COO. Okay, now this is a salt, and if you guys remember from your solubility rules, specifically this is a strong electrolyte. Okay, which means it has almost complete dissociation. So if you guys want to make a quick note, the weak acid is going to have a partial ionization. So only some of the acetic acid molecules will ionize, but all of the salt will ionize. Yeah, pretty much, yeah. Dissociation is when they dissociate, so separate. Ionization is when you basically break them up into ions. Yeah, you can still have dissociation, yeah.
So, I just want to mention, like, when we try to find the salt,
Yeah.
it's the first 2 columns and the second column that's heavier?
Yes.
That's how you...
That's the easiest way to think about it, yeah.
Okay, because, like, I was going to say, like, it's not just sodium. That's like,
not just sodium, no.
Okay.
Like potassium, things like that as well.
Okay.
Yeah.
Do we have to have those strong electrolytes?
There were the solubility rules that you guys need to memorize. All of the first column, those things are going to create strong electrolytes, and ammonia and nitrate. Yeah, it's in unit 4. I think I mentioned it. It's like only 2 rules you need to know. All right. So this is going to inform us about what's going on here, because you got a weak acid and a strong electrolyte. So since this guy is going to completely ionize, what it's going to do is it's going to affect the weak acid dissociation. Okay, and let's talk about why it does that. So what we're going to do first is we're going to write the dissociation equation for the weak acid. So I'll give you guys a minute. I want you guys to write the dissociation reaction for your weak acid. We're going to do an ice table with this, so just keep that in mind. But write down the equation for how this weak acid is going to dissociate. Alright, so we got that for our dissociation equation. Now, we're going to do an ice table underneath, so let's set up our ice table, and I'm going to explain why the strong electrolyte is going to affect the dissociation. Okay, so let's start with the initial value of our acid. It tells us that our solution is made with 0.3 moles in 1 liter, so that's 0.3 molarity. So our initial molarity for our acid is going to be 0.3 molarity. Okay. Our hydrogen is going to be 0. Okay, but we're going to actually start with some acetate, because if you guys notice, we also have 0.3 moles of our sodium acetate. Now, we said that sodium acetate is a strong electrolyte, so it's going to completely ionize, right? So we're going to start with 0.3 molarity of our sodium acetate. Exactly. So this is going to break down into 0.3 molarity Na+, and it's going to break down into 0.3 molarity CH3COO-. And that's why it's called the common ion effect. They have an ion in common, so the salt is going to affect the dissociation of our acid. Okay, so you're going to start with 0.3 molarity of your acetate as well. So you never need to use quadratic. So let me go over it. So you're going to lose some acid because you need to create hydrogen, right? So you're going to gain X and gain X on this side. And then for your equilibrium values, you'll get 0.3 minus X, you'll get X, and you'll get 0.3 plus X. So far, so good for the ice table? Okay, so this is where we go into, we have to figure solve for X using Ka. So Ka is equal to the concentration of H plus times the concentration of the acetate divided by the concentration of our acid. I'm not going to write all that, I'm just going to write HA. Okay. Alright, so let's plug in our values. So Ka is going to be 1.8 times 10 to the negative 5 equals, we got X on the top times 0.3 plus X divided by 0.3 minus x on the bottom. Okay, and then you guys can see this is probably going to lead to a quadratic. However, we can use the 5% rule, and so we can get rid of the ones that are negligible. So let's talk about what the negligible things are. Yeah. What do you mean? Yeah, because H plus was given to you using the pH. See the difference? The difference here is you're looking for pH, but in the previous problem you were given pH so that you could solve for what x is. You were given the ability to find x on your own. All right, so for the 5% rule, we just need a for the 5% rule, it's basically telling us the change is negligible, and so we can actually assume that both this change and this change is negligible because they're the same value, right? It's going to be minus x and plus x. The amount that you lose of this is going to be the same as this. So you can actually cancel out the x's here using the 5% rule. We still need to keep this x because we need something to solve for. This one right here, because we're trying to find pH, and to find pH you need this value right here. Honestly, no, you don't have to. We're just getting rid of those two because it makes the math easier. Yeah, the real trick of 5% rule is figuring out what's going to make your calculation the easiest. You just need to have one x left in there to solve for. Yeah. It shouldn't make a big difference. Which x did you keep? This one right here? Yeah, so you can't, so you don't want to keep the plus x because you got to distribute, that'll give you x squared and an x. That's a quadratic you need to solve, so you want to avoid that. You could keep the minus x on the bottom, but if you solve it, I believe, I just did it actually. You'll get 5.4 times 10 to the negative 6, which won't even show up in your significant figure, so you can just ignore it, just skip that step. Okay. So this is one of the tricks of using the 5% rule, is to figure out what is the best thing to get rid of for yourself. Okay. All right, so from there, if you get rid of those x's, you guys see how there's 0.3 on the top and bottom? Makes it really easy. They cancel out. And then you're going to end up with x is equal to 1.8 times 10 to the negative 5. Okay, and then you can plug this back into your ice table and then solve for pH. So I'll give you a minute to solve for pH and finish up the problem. And then this would be a good time if you have any questions or confusion, because I know that is a little bit weird. It's a good time to ask. All right, so pH is 4.74. All right, you guys think you could try one on your own? Okay. Well, I'll give you a couple moments. I will give you guys this one right here. I will let you guys know I'll let you guys know off the bat that this is a strong electrolyte, right? Because it has potassium on it. Alkali metal salts are going to be strong electrolytes, so that's my trick to you. But go ahead, see if you guys solve it. If you have questions, come up and ask me. I'm more than happy to help you guys out, but I'll give you guys about 5 minutes to solve this out. Very similar to the previous problem. All right, guys, so I got the answer up there if you guys want to check your answers. If you got something around 5.4, that's fine. Somewhere around there. So for the previous two examples, we were looking at a weak acid and how the dissociation is affected by a strong electrolyte. Okay, so we're going to stay on weak acids, but we're going to look at how a different compound can affect its dissociation. Okay, so we are going to look at this problem right here. You have HF, and what type of compound is HF? Nope. Weak acid, yeah. This is the one tricky one that they're going to mess with you, weak acid. And then they give you a different compound, HCl. What type of compound is HCl? Strong acid, yeah. Good, I'm glad you guys are memorizing. Okay, well, it's good to know. So, we got a weak acid and strong acid. Now, I know that it's not an electrolyte, but if you think about it, a strong acid pretty much acts like a strong electrolyte, right? Because the key thing about a strong acid is this guy also has complete ionization. Okay? So you can think of it the same way. Now, it's going to change one more thing on your ice table, but I'll let you guys try thinking about that and figuring it out. I'll give you guys about 5 minutes or so to solve this problem. And look at the question and be very careful of what we're solving for this time, okay? So a little bit different from the previous problems, but same kind of steps. So I'll give you guys a couple minutes, and then we'll go over it together. Alrighty, guys. So I got the answer up there. You are first looking for the fluoride ion concentration, and so we can do the ice table. So the one thing that's different about this problem is that the common ion is hydrogen, right? So it's the cation that is the common ion, not the anion. So you should have gotten 0.1 for your hydrogen. And then from there, you just solve it the same way we've been doing, minus x on the reactant side, plus x for the products. And then we can plug it into the Ka expression. Same thing, you can cancel out the x's that make it difficult for you using the 5% rule, and then you solve for 0.0014. You plug it back in. For fluoride ion, you don't need to change anything because it's just x, right? So you just write it down. For the pH, you're going to have to add 0.1 with the x in order to get this right here. But honestly, even if you didn't do that, you'll get a number very comparable to it. So it's not going to make a big deal. But something around 1, something around 0.99 should be good for your pH. Okay. Just make sure you read your question carefully because this was asking for two things. On the AP test, sometimes it will ask for multiple values for a FRQ, so just make sure you answer all the components of the question. All right? Yes, there is partial credit. I'll actually show you right now we're going to take our break. But let's take a 5-minute break real quick, and then we'll come back. Okay, so we only have 2 topics left for this unit, but they are kind of dense topics, so we'll probably not get through the whole thing for this topic today. Just keep that in mind. But the next topic we're going to be talking about is something called a buffer. Okay, now I'm going to have you guys write this on. I'm going to type it up on the screen actually, just to make it a TLDR because I don't want to go through the entire reading part of it. Okay, so a buffer is basically a solution that resists drastic pH changes. Okay, so it's basically a solution that even if you add an acid or you add a base to it, the pH is not going to change really drastically. Okay, so we see buffers a lot in biological things like right? In your blood. Blood is a good example of of a buffer because you don't want the pH changing drastically, right? When you in something that's alive, because that'll mess up all your chemical reactions. Okay, and the way that buffers work is they can get very complex, like your blood is a very complex buffer system, but the super simple one that we're going to look at, there's 2 different types of buffer. Okay, the first is a solution that contains a weak acid and its conjugate base, and the second type is the opposite. It's a weak base and its conjugate acid. Okay, so those are the 2 different types of buffers. Okay, but they pretty much function the same way. Yes. No, so water is going to be the solvent, but water is not a buffer. I know it auto-ionizes, but water is going to have drastic pH change. That's why we use it as a solvent for acids and bases. Yeah, great question though. And I'll talk about how this works in just a second. But it's going to be one of these 2. It's going to be an acid and its conjugate base, a base and its conjugate acid. All right, so let's talk about just very quickly how a buffer is going to work. So let's just do a simple example. So we're going to take the first example, but it's going to apply to the second. But let's say that you have a buffer solution, and a good example of a buffer solution would be something like HF, so a weak acid, and its conjugate base, so F minus. Okay, now, the F minus can be present in different forms. You could have just the ion, or you can have a salt that'll produce F minus, so something like NaF. Okay, either or. Basically, anything that can produce F minus. Okay. Everybody good on what a buffer is? Again, this is what it's generally going to look like. You can also have a weak base and its conjugate, but just look for the conjugate. All right, so the way that this is going to work is, let's say, so this right here is a weak acid and its conjugate base. So this right here is going to have a certain pH. And let's just say, for example, we're going to add an acid to it. So let's say we add an acid. So let's say we add HCl. Actually, let's make it more general, H+. Okay, because that's what makes things acidic. Okay, so you add H+. God bless you. So if you add H+, okay, you have a solution that has HF and F- inside of it, right? Now, typically, let's say we didn't have the conjugate base. If you add H+, the pH is going to drop drastically, right? Because you're increasing the concentration of H+. However, if you have F- and you add H+, what's going to happen is these guys are going to see each other. And remember Chandelier's principle, right? If you have your reaction right here in equilibrium, and all of a sudden you add a bunch of H+, excuse me. If you add a bunch of H+, which way is equilibrium going to shift? To the left. So the solution is going to be like, oh my gosh, we have so much H+, we gotta bring down that ratio. So it's going to start producing HF. And that's pretty much how a buffer works. Okay? You have a acid and its conjugate, and so even if you add another acid, it's going to start shifting the equilibrium back where you got it. Okay?
So are most solutions buffers then? If it's like at equilibrium, does it mean it's a buffer?
Yes, but you need a sufficient concentration of the conjugate. Because remember, HF is a weak acid, so the concentration of the product is going to be pretty low. So you need more of it from somewhere, usually a salt.
So if you have HF, if you have an equilibrium equation, and that therefore the Chatelier's principle applies, like, would it be a buffer?
Sorry, I didn't understand that. Let me answer your question later. Is that okay?
Yeah. Sorry.
Yes.
So the pH will change a little bit, but
Yes.
you're making more weak acid.
That's correct.
Than
Yeah.
putting in a strong acid.
That's correct. Yeah. So it basically, it's like it buffers. That's where we get that term. It buffers the pH change. It basically slows it down. Eventually, it will change it drastically, and we'll look at the calculations for that. But initially, it'll slow down the pH change. Yeah. Yeah, it's exactly Chandelier's principle. It's going to shift depending on which one is added. Yeah. All right, so that's if you add an acid. Let's say that we add a base. Okay, so we add we add OH minus. Okay, so if we add OH minus, what do you think that it's going to react with? Yeah, HF. HF will react with the OH minus, and that'll also reduce the pH change, because if you react HF and OH minus, it's going to produce water. Sorry, I'll write it the other way. HOH. It'll produce water and F minus. And water is neutral, so it's not going to change the pH very much. And so that's how it buffers the pH change. That's the mechanics of how it works. But just know that you need a weak acid and its conjugate base. Okay, that's kind of the simple way of understanding how a buffer is going to work. Okay, obviously, we're going to go into more detail, and it does get a little bit more complicated once we start adding to math, but that's a general idea of what happens. Okay, so those are buffers. So I want you guys to take a look at 1254, and we got 3 different pairs of solutions, and I want you guys to take a look at each one and just write down if you think it's going to act as a buffer or not. So you're going to write yes or no, and then just write a quick explanation of why you think it will act as a buffer or why it won't. Alright guys, so let's go over these. So let's start with A. If you guys take a look right here, the answer for this one is yes, this will function as a buffer. Okay, and if you guys take a look, it's because it shares a common ion right there. Okay, so this is your acid, this is the conjugate base. If you look, it's just the same thing minus the hydrogen. Okay. Alright, you take a look at B. This is also, yes, this is going to act as a buffer, because if you take a look, you have carbonate as your conjugate base. Again, this is just minus the hydrogen. Okay, so C is actually going to be no. Does anyone want to take a shot at why it's no? Yeah. Exactly. Yeah, this is because HNO3 is a strong acid. So again, this is why you want to memorize your strong acids. Because if you guys remember, you want a weak acid because you can't. If you have a NO3 floating around the solution, you add an acid, it's not going to reform HNO3 because it's a strong acid. So that's the reason why. Okay. No, because HNO3 is a strong acid. Yes. Okay, so moving on. This is all stuff about how we know it works, what we generally talked about. If you guys want to go more into detail with the reading, you can, but it's pretty much summarizing the thing that we went into. Yeah, what's up? All right, so this table right here, or this chart, kind of explains what we talked about. So this is going to be our buffer. So if you guys want to make a little note about this chart right here, it's in your textbook as well, 17.2. But this kind of visual helps you visualize what a buffer is. So this is your buffer. You're going to have a certain concentration of HF and F minus. If you add an acid, the concentration of your acid is going to go up and your F minus is going to go down. And the reason why is it's reacting. The F minus is going to react to produce HF, and that's how it buffers the pH. If you add a base, your anion concentration is going to go up and your HF is going to go down because the HF is going to react with the OH minus in order to buffer the solution. So this is a relationship that you want to be able to know as well. For a buffer, if you add acid, obviously the acid concentration goes up. But if you add a base, the conjugate base concentration will go up. Okay? So that's just a relationship that you want to keep in mind. All right, so we will end by looking at number 55. So I'll give you guys a couple minutes. Try 55. You're going to have two reactions that you need to write. What happens when NaOH is added to this buffer solution? So this is your buffer right here. You're adding a base, and you're going to write the equation for that. And I also want you to write the equation for what happens when you add acid to this buffer solution. Okay, so let's start with the base. So our added base is NaOH, and the added base is going to react with the acid in the buffer, right? Because acids and bases react. And then what it's going to form is, the first thing it's going to form is your cation, right? Na+. But it's also going to form your conjugate base, because what's going to happen is the hydroxide from your base is going to react with the hydrogen from your weak acid to form water, and so what you have left over is the conjugate base. So keep that in mind. If you add a base, it's going to result in an increase in the conjugate base concentration, okay? Because that's what it makes. If you add an acid, it's going to react with the conjugate base, because again, acids and bases react. You're going to make Cl minus, and you're going to form the weak acid. So the relationship is, if you add an acid, you're going to increase the weak acid concentration in your buffer. Okay, so this is kind of the point of these problems, is to figure out these two relationships. Okay, if you add a base to a buffer, it'll increase your conjugate base concentration. If you add an acid, it's going to increase the weak acid concentration. And this is what was in the diagram that I pointed out earlier above on the document. But this is the reaction why that happens.